Go. Hello, Mr. Aaron, Mr. Ryan, are you right? Yeah, we talk about a game theory this few days. We talk about Minimax. Yeah, Minimax.
Minimax. We talked about NegaMax.
No. And we talked
Yes,
about
we are.
alpha, beta pruning yesterday, yeah?
Alpha, beta, pruning.
Yeah.
Today,
Alpha, beta pruning. Yeah? Pruning.
pruning.
So alpha, beta pruning, we talked about that yesterday. It's basically this improvement of the Minimax. Yeah? Minimax. What's Minimax? It's a what's it? What's about it? The Minimax. You know. Minimax, yeah, something on a game tree, yeah, game tree. So for example, this player, as the point of this player's view, he's trying to maximize it. For example, yeah, maximize it. And then the other player takes them. This is two players zero sum game, and he's trying to minimize it. Yeah, for example, this is 10A 11, and then if we are minimizing at this level, so it will be 8. And then if this is the 6, 3, 4, if we're trying to minimize it, there will be 3. And then here we're trying to maximize it, there will be 8, right? Yeah? Remember this? Yeah? And we talk about alpha beta pruning. Yeah? What's alpha beta pruning? Just a little bit review, okay? What's alpha beta pruning? So what's the special about alpha beta pruning?
It has more glitter.
How? Look, 3.
But not even.
So we are trying to maximize 5 here. Yeah. This is maximize, and then okay. Okay. So what's the value of here? What's the value of here?
5.
This is trying to minimize it. Yeah. 5. Why is that? Can anybody tell me?
It's because, yeah, if you use your brain.
Why we don't need to calculate the values in this?
Because we see a 6.
We say 6. So what's this value? This x here is what? X here is what?
Must be 6 or over.
X is bigger than 6 over. If this is 6 or over, and we are trying to get a minimum, 5 is the winner here. So we don't care anything. We don't care the values here, right? Because it's uninteresting. Yeah? It's uninteresting to us. Make sense? Yeah? Look, this could be a huge subtree here. And at this point, because we're evaluating the tree from left to the right, and we find the value 6 here, then we ask ourselves, do we need to continue searching here? No. Why is that? Because if this is 6, the parent value is trying to maximize, so these values must be 6 or over. If it is this value is 6 or over, and then this value is trying to minimize this, we have a better value, which is 5. No matter what values here, this is 6 or over, and then this will be 5. Okay, this is alpha beta pruning. Okay. So it will help us to speed up the search, yeah, search on the trees. Okay. Okay, so let's go back to this Minimax thing. So Minimax thing. So let me just quickly write the implementation of Minimax. Okay. Define min max. So we have current state, we have a depth, and we have a turn. Okay, so sometimes we call it color. Okay, turn, player, whatever. So let's just try to maybe we can say maximize it. Yeah. So this is basically a Boolean value here. This is a Boolean value. Yeah, indicating if we are trying to maximize or minimize the color, blue or red, or the player, agent or opponent. Okay, so they are playing against each other. So this value, Boolean value, is used to indicate whether we are trying to maximize or minimize in this case. And these steps, we don't actually need to provide these steps here, but we are given we provide a depth value so that we can terminate earlier, right? So if we don't provide these steps, then only the leaf nodes of the leaf node, the game tree may be so deep, right? Yeah. If you're playing a chess, usually how many moves before a checkmate?
1.
No. For the tic-tac-toe, yeah? Tic-tac-toe, how many moves
2.
to
3.
for a game of the tic-tac-toe to be fully ended? Usually.
It needs to be 3 in a row.
Yeah, I
If
know,
you
but how many
find out-
moves? How many turns? The depth, how many turns?
3.
Why is it 3? No,
6.
6? What I'm asking is that, you know the tic-tac-toe game tree?
4, 4, 4.
No, listen up. Listen to the question carefully. This is game tree, yeah? This is the root, 0. Depth is 0. And then if I make a cross here, yeah? I make a cross. So I put it here. And then the other player put a circle here. Yeah. So usually how many moves before this game is ended? Yeah.
4, 5.
If two players played smartly, intelligently, you know the draw.
Well, it's only
9, yes, 9. Yeah, because look, this game is so small, and then if each player is smart enough, does not make stupid mistakes, and then the depth will be 9, right? This is what I mean, the depth will be 9. But for a chess, maybe 30 moves, 40 or more, and the depth will be huge. Considering branching factor, you know the branching factor. The branching factor here is 9. It's basically the maximum number of kids for a state, right? Because I'm standing at the root, and I have 9 kids, right? I have 9 kids. Why is that? If I'm at the root, I have 9 kids. Right? Because I have 9 choice to press to put the cross. Make sense? This is called branching factor, okay? So if the branching factor is considering, if the depth is huge, then the search tree, the search space will be huge. That's why we put a depth limit. Depth. So for example, if let's say, we only consider the steps up to maybe 5 or 6, right? Okay. So one way you can call this function with the 0, and then you increase up to a maximum depth, which is maybe 6, then you terminate. Or you can give a value 6 and then you decrement until 0, then you evaluate it. Okay, so that's what the depth is for, okay? Okay, so now at the beginning we just need to evaluate it. So we can say, okay, let's say we give a value from the positive depth. So if depth equal 0, right? Or the state is end state. So it's end state. Then we return the value, evaluate the score of the. I want to put the utility function here, but utility function only applies to end state. So let's change it to return the value, evaluate score of the state. Okay. Okay. Right. This is then look, if we are maximizing it. If this player is trying to maximize, then I have a score, which at the beginning I put it to minus infinity, okay? Minus infinity. And then I can say for action, in action state, okay? Action state. So the action is like the kit of the state, of the current node, okay? Sometimes we call it node, and then this will be kit, children. Right, and then score will be equals the maximum. We are trying to maximize it. Score, and then we call this Minimax function. Minimax function state, the new state. Yeah? Let's say we have a new state. So that will be the action, new state. So that will be successor of the action of the state, and the new action. The depth will be, let's say, depth will be -1, right? And then maximizing it. If we are maximizing it, now the next turn will be minimizing it. Okay, simple. And then return score. Okay, this is maximize. And then minimizing is similar. So instead of negative infinity, here is the positive infinity. Come on. And then for action, in actions. Yeah, this is the same. Come on, can you see this part? Can you understand this part? Come on. Score equals minimize. Okay, we are at now minimizing it, right? Min max.
We're good at Maniac.
And then this will be the same. Success, state, action, depth -1. And look, we are minimizing it, so the next term will be maximizing it. Okay, so next term I need to put pass the true here, right? And then return score. Okay? Look, this is the min max. Min max. Maximizing, minimizing. These two parts quite similar, yeah? The only difference is what? The score, if we are maximizing it, the initial score is negative infinity. If we are trying to maximize it, trying to minimize, the initial score is maximum infinity, yeah? Make sense?
Mm-hmm.
Right? And then, I mean, that's can we improve this? One problem of this implementation. Can you pick a problem of this implementation? What I'm saying is there anything you don't like about this approach? Anything? Is there anything you don't like about this implementation? I mean, this works, but come on, be picky. Which part you don't like?
It looks
kind of what?
slow.
Yeah, it's slow. Yeah, it's slow. Obviously, because we have you learn the alpha beta pruning. Yeah, that's a very good point. But what I'm saying is this. Consider this and this. What?
There's a lot of writing.
That's a lot of writing. Why is there a lot of writing? Okay, come on. You're quite close to the answer. What I want.
Because
Do you see these two pages?
because you because you write the same thing but the opposite again.
Well done. Okay, that's exactly what we are looking for. Similar thing, the same thing, but the opposite. Yeah. This is kind of awkward, right? It's not very simplified, right? It's kind of tedious because these two is similar. It just as a different player. This player is trying to maximize. This trying to minimize, and we have to write two parts. Yeah. At least these two block of code looks quite similar. The logic quite similar. Yeah? One is trying to maximize, the other one minimize. Okay, so today we're going to talk about another approach which is called NegaMax. To simplify these two branches. Okay? So what does it mean? Okay, so look at this. If there are two values, A and B, right? I want to get the maximum of this value, A and B. Come on, look at me. Look at here. Okay.
So
Yeah, A and B, two values. I want to get the maximum. It's equals to minimize. Look, I put some negative sign here. Min minus A minus B. Okay.
and C and D and
Yeah?
E and G.
Look. Can we give an example like A equals 50, B equals 100? So what's this answer? Which is maximum? 100, right?
Yeah.
So it equals minus min minus 50 minus 100. So which one is smaller? Minus 50 or minus 100?
Minus 100.
Minus 100. And I put a sign. Minus 100, which is 100. Okay? This is the same thing. Okay? Yeah? We can prove this more precisely. Why is that? Look, if A is bigger than B. Okay, because look, max A and B. If I say A is bigger or equal than B, okay, so max AB equals A, right? Now, if A is bigger than B, if I put the negative sign, so minus A is smaller or equal minus B, right? Yeah? Yeah? Alright? So minus A is smaller than minus B. I want to get a minimum, so it's minus A. So actually this one is minus A. So I put another A minus, that will be, that will cancel out, so it will be A. It's the same thing. So we just prove it, okay? So if look based on this, then we can change this. How can we change this? First of all, let's change the function. Okay. Do we have a color of other pen? Other pen with other colors.
I got red pen.
Can I have it, please?
I don't have it.
Okay, that's fine. NegaMax.
NegaMax.
Okay. So stay, we keep it. Depth, we keep it. Maximizing it. Maximizing it. Do we need to keep it? Do we need to keep this maximizing it?
Maybe we do.
Okay, so
I think we do.
this is the same, yeah. Depth equals 0 or xn is 0. So we don't need to write this, right? But we keep this. We can erase this bit. Okay, look, we can erase this bit. So at the beginning, score is negative infinity, and then this is the same. Now look, NegaMax here. So I just have to do what? I just have to put a sign here, right? Put a sign,
Blah.
and that will be it. Yeah?
That will be it.
Yeah, that will be it. Yeah, do you understand? Yeah. Do you understand? I think that will be it. Yeah.
That's
What did I just do? What did I just do, Eric?
just change the.
Which bit? What changes did I make to bring to make the Minimax into NegaMax? Look, it's simplified.
You put it at the end of that thing.
What line of anything?
Score equals max.
Score equals infinity.
Yeah, I just look as this NegaMax is trying to maximize the value, right? The only difference is that when I pass it to the next player, I put a sign negative. I put a sign negative, and that will be it. Yeah. Look, why is that? As I said, look, if I want to maximize A and B, this is the same thing as what? If I put a negative sign, right? Yeah. Yeah. So you'll be a lot simpler, right? You'll be a lot simpler, right? Yeah. Because now this one is trying to maximize, and then the other one is trying to minimize. As the other player's point of view, the higher value of this current score, yeah, is lower. Is lower. Is look. This is the line, right? Okay. So the higher of this A, okay. If this A goes to the right, the higher value is further away from the other player, right? Make sense? Yeah. Look, because this each two player takes turn, right? If as the first player is trying to maximize it, so the first player is Asian, right? The higher value, if the score is goes to the right, it's more preferable for the Asian. If it's more preferable to the Asian, then it'll be less preferable for the opponent, right? But the thing is that this function is always trying to maximize it. So how can I do this? If it's so it's more higher, then I put a sign. And as the other player's point of view, it's the same. Do you get it? So this function deals both cases, right? The higher value, the better. Yeah, the higher value, the better. Do you get it? Previously, the Minimax function, the agent trying to maximize, opponent trying to minimize. But now, if I put a sign, so both players trying to maximize. But how does that work? Why is that? Because when I pass it to the next one, 100 will become minus 100, right? Yeah, 100 is good for me. It's bad for you, because I put a sign minus, and it will become minus 100. Right? Do you see this point? I just put a negative sign. This here. I know it. This function is trying to handle both cases. Okay? Yeah? And we okay, so can you tell me what's this depth function? Depth equals 0 equals, what does it mean? What's this depth?
It's
Why do we need this?
because we like if it's like over
Yeah, over. Yeah.
yeah, and
It's a depth limit search. Remember this search
like
tree?
you can only go around a limited section.
Yeah. Look, I don't care what happens because this tree may be huge. Yeah, you go more and more and more, and there are lots of to do here. But all I can do, all with my computational resources, all I can do is to search for the maximum depth of 4, 5, 6 or whatever, and I set a hard stop. Okay? Yeah. Make sense? Okay. So that's it. Bye bye. Bye bye. Say bye bye, Ryan.
Bye, 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 bye.